New in SimCenter Femap 2022.1 is the support for Solution 402 Kinematic Joints. Kinematic joints allow structural analyses of an assembly containing moving parts. These kinematic joints will be stored under the Simulation Entities branch in the model info tree. And users can create various joint types such as revolute, inline, slider, spherical, cylindrical, slider universal, fixed, screw, universal, and constant velocity. In this model, I have 4 revolute joints connecting the suspension linkage on the rear of this mountain bike. So 1, 2, 3, and 4 revolute joints, and this allows me to connect the different pieces of the assembly, but also allow them to rotate. So I've already solved this model, and what I'm going to do now is animate the deformation of the rear suspension travel. And you can see as the frame articulates that the revolute joints connect the geometry, the parts in the assembly, but again allow them to rotate about the pieces at the point of the revolute joint. There has also been the addition of kinematic connections, and what these kinematic connections do is basically speed up the process to create kinematic joints. So let's say I want to create a revolute joint on this side of my universal joint geometry here, and I'm just going to do it to ground because it's attached to nothing on this open end, and I'm going to connect the motion attachment as a surface here, and it will automatically generate me a coordinate system in the axis that I need it to, along with the point of the joint location as well. And under joint properties, I can specify some of the more technical things like translational stiffness and rotational stiffness and others depending on what type of joint it is. And in general, I can set some of the expansion methods. So as I selected a surface, I can choose the specifics, so whether it expands out to the nodes on the boundary only or just the interior or both. So I will leave it at boundary only. And for Nastran, we can also specify what type of element connects the joint to the mesh. So in this case, I will do the C joint and RB2s to connect to my mesh there once I've meshed it. So as you can see, once I've created this, it creates my coordinate system and my joint as well. So I'm going to repeat my process and create another connection, this time it being a universal. And I'm going to go ahead and use my surfaces to select the holes of each clevis. And this time I already have my coordinate systems created. So in this case, I want the number 100 here with the x-axis aligned. And I'll repeat with the other side. And create that one. And to drive the motion of the simulation, I'm going to put a driver load on that revolute joint. So I'll make it 360 degrees, radians, and go ahead and select my revolute joint. And now all I have to do is create one more kinematic connection at this side, mesh my part, and I'll be ready to solve. And just to finish up here, I will animate the deformation of one revolution of this universal joint.